In the next module, we're going to begin discussing what is Cisco ACI. We'll begin taking a look at what is overlay networking, or SDN, as a primer. Take a look at some overview and terminology of Cisco ACI. Talk about the question, what problems are we really trying to solve here? Take a look at the logical model, and then an overview of the concrete model in Cisco ACI. So to begin with, we'll talk about SDN, or overlay networking, and just go through a brief primer. So as you've no doubt understood by now, there are many new industry trends that are affecting the data center. Things such as cloud services, be it Amazon Web Services, Microsoft Azure Cloud, DigitalOcean, or any of the big players out there. Big data is playing a big change in our data centers these days. Things like Hadoop, Map and Reduce, Mongo Database. DevOps culture is making a huge change. Automation tools, things such as Ansible, Chef, Puppet, GitHub, Jenkins, and continuous integration. And the overarching umbrella that we'll talk a lot more about, which is SDN. So first of all, what is SDN? Well, many people say that it stands for still don't know. But of course, this really means software-defined networking. Now the problem is, a lot of people describe this in different ways. In the same way that if you ask 15 different people what is the cloud, you'll get 15 different answers. If you ask 100 people what is SDN, you're going to get 100 different answers. So first of all, we have the notion that the control plane and data plane are now being controlled by some sort of centralized controller, and OpenFlow was really the first to market with this. We have the idea or concept of network virtualization, or NFV, network virtualization functions. Things such as VMware acquiring Nicira, New Age, Plum, Midakura. And then we have people that call SDN just pure programmability. So Arista or Cumulus have APIs, of course, for their switches. Doesn't necessarily make it SDN, but again, a lot of people would claim that that is SDN. So there's a myriad of different definitions, and they all kind of fall under this umbrella when you ask different people for what is SDN. So let's talk briefly about software overlays, or network virtualization. The concept is that we run a layer 3 routed, non-blocking ECMP, or equal cost multipath fabric, or CLOS fabric, as our underlying infrastructure. And on top of that, we place multiple virtual networks. And these virtual networks are use case driven. So as someone needs a new virtual network, we place a new virtual network on top of the existing hardware infrastructure, using encapsulation methods such as VXLAN, or Microsoft tends to favor NVGRE. So this is encapsulated traffic that's carried over the CLOS fabric. Now, of course, if this is pure encapsulated traffic and the underlying hardware isn't, let's say, VXLAN or NVGRE header ready, then we're not going to quite get wire speed routing or switching. So we need that underlying infrastructure to be, well, it doesn't have to be, but in order to get wire speed packet forwarding, we do have to have that underlying architecture able to read, decode, and forward based on VXLAN or NVGRE headers. So Cisco ACI, talk about some overview and terminology. So first of all, what is ACI? Well, ACI stands for the Application-Centric Infrastructure. And what we're going to begin talking about is how Cisco has built an SDN controller, centralized controller, that has distributed functions, declarative model language, rather than imperative, and we'll talk about the differences there, centered around, entirely based around the most important thing in your data center, which is, of course, the application. So ACI introduces logical network provisioning of stateless hardware. So the idea is that we model an application. Here you see our outside users coming from a particular tenant or VRF, going through some sort of either QoS or possibly firewall, possibly load balancer, hitting our web tier, going then through some other sort of service appliance, again, possibly another firewall, most probably another load balancer, hitting the application tier, so things such as Tomcat is a pretty common one, could be IBM, WebSphere, could be a lot of different application middleware, and then going through possibly some sort of another filter, maybe a stateful or stateless firewall built into the network, or again, possibly actually being a hardware-based or even virtual full next generation firewall. And then hitting the database. Now the database, a lot of times people run databases as bare metal machines. Of course, they could be VMs, but performance tends to dictate bare metal for databases. Cisco ACI doesn't really care whether you have virtual machines or bare metal. We can play nicely with all of them and switch all of it, of course, at wire speed. Now everything is programmed, provisioned, and initially controlled, essentially, through the APIC. Now the APIC for ACI is the Application Policy Infrastructure Controller. So I'm not going to enumerate the naming convention of this much more, but I do just want to be clear. ACI is the entire fabric. This is the APIC controller along with the actual fabric itself, which are the hardware switches. So ACI is the application-centric infrastructure. The APIC, or Application Policy Infrastructure Controller, is where we provision and where all of our configuration essentially takes place. And it's what then dictates out to the rest of the hardware switches, the fabric, what should be provisioned. And of course, we have an integrated VXLAN overlay. So all of the switches recognize, understand, and can forward at line rate our VXLAN headers. And of course, we work with NVGRE headers as well. In the back, and we'll talk a lot more about the encapsulations that we support, especially as we begin talking about Microsoft Hyper-V in a much later section. But it is important to note that when we get inside the fabric, so once we've come from the southbound switch, from the southbound server, be it a hypervisor with VMs, or be it a bare metal machine, or a router, or another switch, like I said, anything, and we come into the south leaf switch, and we'll go over an actual topology and packet forwarding here in a little while. But once we come into this leaf switch, whatever encapsulation was being sent to our leaf switch from the southbound device gets stripped, and we encapsulate everything in VXLAN. And we call this the iVXLAN or inner VXLAN. And the reason we use the differentiation of I or inner is because it's possible that we were actually seeing VXLAN from the southbound device as well. It's possible it's speaking VXLAN. We would map that to one of our VXLAN logical networks or bridge domains, as we'll go into much more detail later, and we would use that. So Cisco ACI uses this idea of a network profile. Again, everything is based on the application, but we need to map that to network constructs. So we basically extend, if you happen to be familiar with at all, Cisco UCS Manager, or the UCS Unified Computing System B-Series chassis blade servers. Of course, the C-Series can work with UCS Manager as well. But the idea of the UCS Manager many years ago brought this idea of abstraction to where we were no longer programming the network card MAC address, the BIOS, the hard drive RAID controller directly on the blade or rack mount server any longer, but we were programming and creating or configuring a abstraction of a service profile, we called it. So we're doing the same thing now in Cisco ACI, but we're doing it with a network profile. And again, this is a stateless definition of the application requirement. So we have our application tiers, any connectivity profiles, which might define, let's say, filters or firewall services inside the fabric, completely self-contained, as well as any external layer 4 through layer 7 services, such as a firewall, be it ASA, Checkpoint, Fortinet, Palo Alto, doesn't really matter, or a load balancer, be it Avinet, F5, Citrix, NetScaler, again, doesn't matter. And we do all of this using RESTful APIs, which we'll talk a lot more about in future modules, but not right now. So suffice it to say this is stored in a flat file format, and we can take our pick. We have either XML, been around for a long time, everyone knows it, or JSON. A little bit more modular, lightweight, easy to read, but we can take our pick based on what we're most familiar or comfortable with, or whatever programming language we want to use. Most programming languages do support both, and we'll certainly talk about some of those, whether it's Python or PHP or even Go or something like that. Almost every modern language supports both XML and JSON as a data format. And if you're not familiar with these, just think of these as a text file, two different types of a text file. The idea is that this is fully abstracted, this network profile, from the infrastructure. So it removes all dependencies of the infrastructure. And it's actually portable across different data center fabrics. In fact, if we create a network profile, let's say we're a consulting company, we would have the ability to use these profiles as templates. And in fact, that's what many contractors or consulting companies do. So we model our applications and then we instantiate them. So we define our application policy model, we define our requirements based on the network profile, and then we instantiate. So what does this mean? When we're ready, we tell the APIC controller to push down. Actually, we tell it when we're building it what kind of deployment to use, whether it's immediate or on demand, and we'll talk a lot more about that later and unpack that. But once we configure it, the APIC pushes this down to the Fabric infrastructure, and it begins provisioning, especially if we're doing on demand, as VMs show up on switches, we begin provisioning these particular or instantiating these profiles. So for instance, a VRF shows up, an SVI shows up, a VXLAN bridge domain shows up. But then, of course, our data centers are largely virtualized, not completely, but largely virtualized these days, so VMs move. And when they do, if we no longer have any resources on a given older switch, let's say this Leaf 1, we take away or remove or really destroy all remnants. So any ACLs, any VRFs, any, let's say, routing protocols typically stay the same because routers typically stay in one place, but we could have virtual routers as well, so it's entirely possible they move. So we remove all the dependencies that require things like CPU, memory resources, and with ACLs, very important TCAM space. So the idea is that all forwarding in the fabric is managed through this application network profile, or ANP, and that IP addresses are fully portable anywhere within the fabric. Security and forwarding are fully decoupled from any physical or virtual network attributes, and devices autonomously update the state of the network based on the configuration policy requirements. So in our network, we have our ACI Fabric, and this is based on a CLOS fabric or CLOS topology. CLOS is not any special type of topology, it's just based on the name, based on the man's last name, Richard CLOS, who created or theorized this type of a bipartite non-blocking architecture actually back in the 50s for AT&T Bell Laboratories, which is where my dad happened to work. Not in 53 when he created it though. My dad wasn't born yet. So anyhow, the idea was built for circuit switching telephony networks. Of course, now we're using this same mathematical non-blocking or statistically non-blocking architecture with packet switching, right? And of course, we're doing layer 3 routing here. So we have our spine layer and we have our leaf layer. Now, some CLOS fabrics do support multi-levels of spines, so a higher aggregation level of spines. And I think we may see that in the future with ACI. But currently, we do only support a single spine layer. So with this spine leaf layer, we call this a 3-stage 2-tier. So the 2 tiers are our spine tier and our leaf tier. And our 3-stage is ingressing at one leaf, hitting any one, basically choosing the equal cost multipath based on, of course, our static hash buckets. And we'll talk about improvements to the fabric that can use or utilize more bandwidth in the future than just our static hashing. But based on our 5-tuple hashing of flows, we'll pick one of the 4 links. I believe the technical terminology is eeny, meeny, miny, mo. At any rate, we ingress through the first leaf. We pick any of the links, and whichever spine we hit, that's the second stage, and then we go out to the final destination, in this case, leaf 5. Okay? So whether we take leaf 1 to spine 1 to leaf 5, leaf 1 to spine 2 to leaf 5, leaf 1 to spine 3 to leaf 5, or leaf 1 to spine 4 to leaf 5, all of them produce a, if you will, a single hop, a single spine hop to get to that egress leaf. And those are our 3 stages: ingress stage, backplane switching stage, and egress. And actually, if you think about this, we're going to talk a lot more about class topologies in the future. So I'll just touch on this right now and then we'll come back to it. But if you think about this, we've actually been doing class topologies for 15 years. You have as well. If you've ever had any sort of a modular switch in your network, even back to the Catalyst, let's say 5500s. Actually, I think that was, the fabric was built in, but still, same thing. Catalyst 6500, Nexus 7000, any modular switch, you have essentially had your line card, your backplane or actually fabric module, and then your egress line card. So if you think about this, these were our fabric modules. If you turn the whole thing sideways, this would be like the line cards in a Cat 6500 or a Nexus 7000. And these would be like the fabric modules. And really that's what we've been doing in our modular switches. So this isn't really a new concept. We're simply extrapolating it from a single physical box into multiple boxes. Now, of course, these could be modular switches as they show. So we almost have multiple encapsulations of, not encapsulations, but stages of a class fabric. Yet anyhow. So then we have our APIC controllers. And the APIC controllers are connected in-band with the actual leaf switches, and we'll talk a lot more about these in the next module. And we always have a trio or 3 APIC servers in our cluster, with the potential of growing up to 31, but a minimum of 3. They have their out-of-band management, we have potential in-band management, and then we connect our servers. Servers could be connected directly, bare metal. They could be hypervisors with VMs. They could be routers and switches. Here we see another switch and then another server on top of this. So there's many different possibilities here. We can certainly support any layer 4 through layer 7 services and external layer 2 bridging or external layer 3 routing. The idea is that we have one logical system to manage with any IP address anywhere. So any host IP address anywhere, but we have one logical system to manage. So we only make a call whether I'm hitting the web user interface to one of the APICs or whether I'm making an API call to one of the APICs. I would simply make that call to one of the APICs. Now I could, if one APIC was down, I could try a secondary or a tertiary, a third server. But the idea is that I'm only making a web change in my user interface or an API call to one of the APICs, and it's provisioning the entire infrastructure. I don't need to go out and touch every single box. In fact, there is no more show run or config T. There's a lot of other show commands. Pretty much every other show command that you're used to in a Nexus switch is there. But there is no more config T or show run. The show run is the configuration on the APIC. And we'll talk a lot more about that because it goes well beyond that of just a regular switch. And then the configuration, of course, is done through the APIC as well.